So welcome back to the session. We will now move to the another important part of the cylindrical insulation system, that is critical thickness of insulation. Whenever we want to reduce the heat transfer, we will add insulation. So a layer is added on a pipe, imagine a steam carrying pipe which is losing heat to the environment, and thereby before the steam reaches the turbine it is getting condensed. So I want to minimize the heat loss, so I will go for adding insulation on it. So when I add insulation like this, the outer surface area increases. Without insulation, the pipe radius is only R1. With insulation, the pipe radius is R2, greater than R1. So it is very important here to note, without insulation, the area available for convective heat transfer from the surface of the cylinder to the environment is 2 pi R1L. When we add insulation, now the area available for convection from the surface into the environment is 2 pi R2L. So because of increase in surface area, the rate of heat transfer increases. Do you understand? Purpose of adding insulation is to reduce the heat transfer. But the moment you add insulation, the exposed surface area to the environment increases, thereby the rate of heat transfer increases. So now if you have an insulation like this, the rate of heat transfer Q is given by the formula delta T, that is the temperature at the surface of this pipe and to the environment, T1 minus T alpha by two resistances. One is conduction resistance and other one is convection resistance. Formula for conduction resistance is 1 by 2 pi KL log R2 by R1. And formula for convective resistance is 1 by HA, that is H naught into outer surface area 2 pi R2L. Now follow carefully. The first term represents conduction resistance. The second term represents convective resistance. As I go on adding insulation, R2 increases. See here, as you go on adding more and more insulation, the R2 value, radius, R2 goes on increases. So as R2 increases, this term increases, so conduction resistance increases. So as you add insulation, it contributes an increase in conduction resistance. But as R2 increases, see here, the R2 is in the denominator, the convective resistance decreases. You got the point now? So when you add insulation, the conduction resistance goes on increases, convective resistance goes on decreases. Initial stages, the decrease in convective resistance is dominant when compared to the addition of conduction resistance. So overall resistance decreases. Because resistance is decreased, heat transfer increases. But as you go on adding R2, after some time, the conduction resistance starts dominating the convective resistance, and hence, as conduction resistance increases more rapidly than decrement in convective resistance, the total resistance increases, so heat transfer rate decreases. If you draw the graph, the rate of heat transfer versus R2 outer radius, you will get a curve like this, which indicates as you go on increasing R2 in positive X direction, the heat transfer first increases, reaches a maximum, and then decreases. The point at which the heat transfer reaches maximum, Q maximum, the corresponding radius is known as critical radius. Critical radius. So we want to identify at which radius the rate of heat transfer becomes maximum. If you look at this curve, the slope of this curve at this maximum point is 0, or this Q, if you take its derivative with respect to R2 and equate to 0, you will get the point where the rate of heat transfer reaches maximum. dQ by dR2 equal to 0. Thermal conductivity of material I am not changing. Length of the pipe I am not changing. Original radius R1 I am not changing. But as I go on adding insulation, R2 goes on changes. So only variable is R2. So if you take the derivative, minus 1 by x square whole term into differentiation of this. 1 by 2 pi KL log R2 derivative 1 by R2, and now this is 1 by 2 pi KL minus log R1, everything is constant, so 0, plus 1 by 2 pi L H0 constant, and 1 by R2 differentiation minus 1 by R2 square equal to 0. This term is not 0, so equating this term to 0, you will get R2 equal to K by H0. And this R2, where the rate of heat transfer reaches maximum, is known as critical radius. Now observe carefully. At this point, the rate of heat transfer reaches maximum, and beyond this, the rate of heat transfer goes on decreases. And up to this point, the rate of heat transfer increases. And the formula for Q is delta T by R conduction plus R convection. As you go on adding insulation, conduction resistance increases, convective resistance decreases. You observe? So, on the left hand side of this curve, this point, maximum point, on the left hand portion of this curve, the convection resistance is dominant. It dominates the conduction resistance, hence as you go on adding radius, resistance goes on decreases, total resistance, hence heat transfer increases. On the right hand side of this curve, the convective resistance goes on, it decreases, and hence you will get a decrement in heat transfer. That means on the right hand side, conduction resistance is more dominant than convective resistance. You understand? So when we provide a critical radius on a cylinder, the rate of heat transfer will become maximum. Beyond critical radius, the rate of heat transfer starts decreasing. Up to critical radius, the rate of heat transfer goes on increases. So if you want to maximize the heat transfer from a cylindrical system, you have to provide critical radius. If you want to minimize the rate of heat transfer from a system, you should see that the point should lie on the right hand portion of this curve. Then adding insulation will reduce the heat transfer. I will repeat. Look at this figure carefully. Suppose the initial point is at this arrow. You add insulation. What happened to the radius? Increases. When radius increases, the Q increases. So if the initial point is lying on the left hand side of this curve, adding insulation will increase the heat transfer. If the initial point is lying, say at this arrow, on the right hand side of this curve, adding insulation will reduce the heat transfer. So you have to be careful while adding insulation. What for you are adding insulation? Are you trying to increase the heat transfer or decrease the heat transfer? If your purpose is to reduce the heat transfer, you should see that the initial point lie on the right hand side. If your purpose is to increase the heat transfer, you should see that the initial point should lie on the left hand side. This is a very important concept in insulating the cylinders, called critical thickness of insulation or critical radius of insulation. In steam carrying pipes, the purpose is to reduce the heat transfer. So whenever you are insulating a steam carrying pipe, you must ascertain that the initial point should lie on the right hand side of this curve. And this increase in heat transfer due to adding insulation is utilized as an advantageous thing in insulating electrical cables. Imagine there is a copper conductor through which current is flowing. Because of the resistance offered by the copper wire, it generates some amount of heat energy. We know Q equal to I square R. Unless this heat is dissipated effectively to the outside environment, the temperature of the wire goes on increases and it may lead to melting of the wires or results in short circuit problems. So the conducting cables are provided with an insulation to avoid the shock, and that insulation, instead of reducing the heat transfer, should promote the heat transfer, thereby the life of the cable will be maximum. So therefore this last sentence is very important. This concept is used to increase the rate of cooling in electrical cables or wires. However, when we intend to reduce the heat loss by adding insulation, like in steam carrying pipe insulation, it is essential that the final radius must be larger than the critical radius. Somewhere here it should. So we'll stop here, and problems on critical thickness of insulation we'll see in the next.